Close your eyes for a second. Picture a dinosaur. You probably saw teeth. Something huge, something that would kill you before you even heard it coming. Now here is the question no one asks. Where did that image come from? Not from science, not from fossils, from a movie, from a toy, from a poster on a wall when you were 7 years old. The real dinosaurs were stranger than that, smarter than that, and in some ways more familiar than you were ready for. Some of them had feathers. Some of them raised their young. Some of them travelled in groups, communicated and chose their targets carefully before attacking. And one family of them, a small, fast, feathered group, survived the asteroid that ended the rest. They are still alive right now. You probably saw one this morning. For 165 million years, these animals hunted, defended, adapted, and dominated every corner of this planet. That is 550 times longer than your entire species has existed. This is not the story of monsters. This is the story of the most successful animals that ever lived. How they ate, how they fought, how they died, and why part of them never actually went away. This is dinosaurs, predators, prey, and survival in the age of giants. You've seen them before, in movies, in museums, in the drawings you made as a child, long before you understood what they really were. Giant creatures with massive teeth, moving through a world that no longer exists. You think you know what they looked like. You think you know what they did. But most of what you picture is wrong. The dinosaurs were not slow, cold-blooded failures waiting to be wiped out by history. They were not the lumbering monsters that movies turned them into. They were something far stranger, far more complex, and the more science unravels the details of their world, the more unsettling the real picture becomes. Because the real picture looks less like a Hollywood nightmare and more like something that is still very much alive today. You are going back, all the way back, to a world that existed before your species, before your genus, before your entire branch of the family tree had even formed. About 230 million years ago, during a period scientists call the Triassic, the first true dinosaurs appeared on Earth. They were not the giants you imagine. They were small. Some were no larger than a turkey, but they had one advantage that the other creatures of their time did not. And whatever that advantage was, and paleontologists still argue about the details, it allowed them to outlast, outcompete, and out-evolve everything else on the planet for the next 165 million years. What exactly gave them the edge? No one fully agrees, and that is exactly what makes the story worth telling. The planet they inherited looked nothing like the one you live on today. The continents were still joined together in one massive landmass called Pangaea. The climate was hot and dry across much of it. The world was still recovering from the Permian extinction, the most catastrophic biological collapse in Earth's history, which had erased more than 90% of all species just 20 million years before. Into that recovering world, the dinosaurs stepped. They did not just survive. They built an empire. For over 160 million years, dinosaurs dominated every major landmass on Earth. To understand how vast that timescale is, consider this. Your entire species, Homo sapiens, has existed for roughly 300,000 years. The dinosaurs had 165 million. They had time enough to evolve into thousands of different forms, to fill every ecological role from top apex predator to the world's largest plant processor, to spread across every continent, including Antarctica, and to build some of the most intricate food webs the planet has ever seen. So, what were they eating? How did they hunt? How did they defend themselves? How did the ecosystem hold together? The fossils have been quietly answering these questions for 2 centuries. Paleontologist Robert Bakker spent decades challenging what the scientific establishment believed about dinosaurs. In the 1970s, his work helped dismantle the old idea that they were slow, cold-blooded reptiles plodding through a prehistoric swamp. What emerged from that revolution was something fundamentally different. Dinosaurs, Bakker argued, were warm-blooded, fast-moving, ecologically sophisticated animals. They behaved more like the lions and elephants of today than like any modern reptile. That shift changed everything, because once you see them that way, their strategies for hunting and survival start to make sense. Let's start with the meat eaters. Tyrannosaurus rex is the obvious place to begin, but the version you carry in your head is probably still wrong. The T-Rex was not the fastest creature in its ecosystem. A large adult, fully grown at about 12 meters in length and 9,000 kilograms in weight, could likely reach a top speed somewhere around 20 to 25 kilometers per hour, roughly the pace of a fast jogger. What it had instead of speed was the most powerful bite force ever measured in a land animal. Scientists have estimated it at between 35,000 and 57,000 newtons. Enough force to crush bone the way your teeth crush a cracker. And it did crush bone. Paleontologist Thomas Holtz, one of the world's leading T-Rex researchers, has spent years analyzing bite marks preserved in the fossilized skeletons of Triceratops and Edmontosaurus. What those marks reveal is that T-Rex was not just a hunter, it was a bone processor. It drove its teeth through solid bone to extract the marrow inside, getting every last calorie from a carcass. It hunted. It scavenged. It took what the moment offered. You do the same thing. When food is difficult to find, you adapt. The T-Rex adapted too. In the Jurassic, roughly 80 million years before T-Rex walked the Earth, the apex predator was Allosaurus. Smaller, about 8 to 12 meters long, it hunted in a world populated by some of the largest animals ever to walk the planet. Brachiosaurus, Diplodocus, Stegosaurus, giants that could weigh 30 to 60 tons, and Allosaurus was hunting them. How do you take down an animal that outweighs you by a factor of 10? You do not use brute force, you use strategy. Paleontologists studying Allosaurus skulls found that its jaws were not built for the crushing bite of T-Rex. They were designed more like a hatchet, a weapon built for fast, slashing strikes that opened massive wounds and caused rapid blood loss. Allosaurus likely attacked the soft tissue of the flanks and neck, then retreated, waiting for exhaustion to finish what the initial strike started. Whether it hunted alone or in coordinated groups remains one of paleontology's great open questions. Then there is Velociraptor, and almost everything the movies told you about it is wrong. The real Velociraptor was roughly the size of a turkey. It weighed about 15 kilograms. It almost certainly had feathers. Evidence of quill knobs has been found on its forearm bones, the same attachment points that modern birds use to anchor wing feathers. It was quick and agile, but its prey was small. Lizards, small mammals, other small animals, not humans, not large dinosaurs. What Velociraptor reveals is something more important than its actual size. The line between dinosaur and bird is not a sharp line. It is a gradient, a slow 165 million year continuum of evolution that connects the feathered theropods of the Jurassic to the sparrows and eagles and pigeons you see outside your window today. Now think about the plant eaters, because they were not passive victims. This surprises most people. The herbivores did not simply stand still and wait to be killed. They evolved some of the most spectacular defensive weapons in the history of animal life on this planet. Triceratops carried 3 horns, 2 long brow horns that could reach over a meter in length, and a broad bony frill. Fossil evidence includes healed bite marks matching T-Rex teeth found on Triceratops bones. That means Triceratops survived attacks. It fought back. Paleontologist Peter Dodson, who has spent his career studying the Ceratopsian family, has documented the extraordinary diversity of horn shapes and frill arrangements across the group, concluding that these structures served multiple purposes: combat defense, species recognition, and display. Stegosaurus carried 4 large bone spikes on its tail, a structure paleontologists now call a thagomizer. Fossilized Allosaurus vertebrae have been found with puncture wounds, matching the exact dimensions of those spikes. The predator attacked. The prey answered. The fossil record preserved that exchange across 150 million years. Ankylosaurus was a living tank, covered from head to toe in thick, bony plates fused directly into its skin. It carried a massive club of solid bone at the end of its tail. A direct strike from that club could shatter the leg bones of any predator in its ecosystem. Nothing reached Ankylosaurus without paying a serious price. And then there were the giants. Brachiosaurus stood about 9 meters tall at the shoulder and stretched to 26 meters in length. It may have weighed 30 to 60 tons. For an animal this large, the primary challenge was not predators. It was fuel. It needed to consume hundreds of kilograms of plant material every single day just to sustain its body. Its long neck was not just a striking silhouette. It was an engineering solution to a caloric problem, a way to reach vegetation at heights no ground-level browser could touch, occupying its own ecological altitude, competing with almost no one. Ecological separation, different species filling different roles, the same logic that governs every modern ecosystem from the African savanna to the Amazon basin. How do scientists piece this together? They know it from the teeth. Sharp, blade-like teeth, built for cutting meat. Flat, ridged teeth, designed for grinding plant fiber. Spoon-shaped teeth for raking leaves from branches. Each tooth reveals diet, where patterns across a lifetime of use reveal even more. They know it from coprolites, fossilized feces. Fragments of crushed bone found inside carnivore coprolites confirm active bone processing. Plant material preserved in herbivore coprolites identifies the species and types of vegetation consumed. The body chemistry locked inside fossilized bone can reveal isotopic signatures tied directly to diet and habitat. They know it from bite marks, from trackways, fossilized footprints left in ancient mud, that show herds of large herbivores moving in formation while lone predator tracks circle the perimeter. The evidence is everywhere. You just need to know how to read it. The food chain in the dinosaur world worked the same way it works in every ecosystem you know today. Sunlight fed the plants. Plants fed the herbivores. Herbivores fed the small carnivores. Small carnivores were hunted by larger ones. Scavengers consumed the remains. Decomposers returned the nutrients to the soil, and the cycle continued, without interruption, for 165 million years. Every creature played its role, even the ones that left no fossils. About 66 million years ago, the cycle broke. An asteroid approximately 10 kilometers wide struck what is now the Yucatan Peninsula of Mexico. The energy released in that impact was equivalent to roughly 10 billion nuclear bombs detonating at once. The blast triggered firestorms across continents. Billions of tons of vaporized rock and dust were hurled into the upper atmosphere. Sunlight was blocked. Global temperatures plummeted. Photosynthesis stopped. The food chains began to unravel from the bottom up. Within thousands or tens of thousands of years, a geological instant, approximately 75% of all species on Earth vanished. The non-avian dinosaurs went with them, but not all the dinosaurs disappeared. One lineage made it through, a group of small, feathered, warm-blooded animals with lightweight, hollow bones, fast metabolisms, and the behavioral flexibility to survive on whatever scraps remained in a shattered world. They endured the cold, they endured the dark. They kept eating, they kept reproducing, and they kept evolving. You call them birds. The next time you watch a crow working out how to retrieve food from a puzzle, or a hawk spiraling on a thermal above an open field, or a heron standing motionless beside a river, you are watching a dinosaur. Not a descendant, a dinosaur, a living member of a lineage that survived the very extinction event that ended the reign of everything else. For 165 million years, their ancestors chased prey across ancient floodplains, defended their eggs from rivals, and adapted to conditions that would have erased almost any other animal group in history. About 230 million years ago, a small creature stepped into a recovering world. It was not the biggest thing there. It was not the most imposing. But something about it was built to last. Something in its biology, its adaptability, its metabolism, gave it the one advantage that matters more than size, more than bite force, more than weaponry. Time. It had 165 million years. It used every one of them. That creature is still alive. It is outside your window right now.